Good morning, everyone. Thank you, Dr. Professor Kagali, for this very kind invitation and the introduction also, very kind introduction. I've looked at the activities of the Karnataka Physics Association, and I'm very glad to do doing this very important and work connecting to the physics teachers and students, especially in the vernacular language. Although I can speak a little bit of Kannada, I don't think I'm a very good speaker, so I would request your permission to stick to English. But I do take the responsibility of communicating to the wider public and students very seriously. I'm a local Malayalam speaker, so I do that a lot in my language. And hopefully in the next 10 years or so, my Kannada would be improved enough so that I can give physics talks in Kannada also. That's my aim, but I'm not there yet.
Very good.
Professor Kagali asked me to talk about the current status of gravitational waves and its implications to our understanding of gravity, dark matter, cosmology, etc. I would do so at the end, but I thought it's a very useful thing to put this in the context of development of modern astronomy. Because I think this is really a part of what is happening in the last 400 years, which was started by Galileo. And we are carrying that flag of Galileo. So that's why I put this title as Galileo and gravitational waves. So most of this is obvious to most of you, so I apologize in advance. All of you know that the story of modern astronomy began about 400 years ago, where Italian mathematician, astronomer, physicist, philosopher, natural philosopher, Galileo Galilei used the telescope to point to the skies. This is an actual image of one of the first telescopes that Galileo made. Of course, this is invented by other people, but Galileo was the first one who used these instruments for astronomical observations. And when he looked at the sky using these telescopes, he made some remarkable observations. These are photographs of Galileo's notebook, and you can see his remarkably beautiful and accurate drawings. Obviously, in the absence of digital photographs and photographic plates, Galileo had to record all these his observations through careful drawings. For example, the left one is his hand drawing of the images of the moon on different days. And he found that, unlike what Greek philosophers thought, as the moon as a luminous blob, it is as imperfect as the surface of the Earth. It has large mountains, craters, and it is reflecting the light of the sun. And you can see how the shadows are moving in the craters, and the shadows of the mountains are moving on the surface, etc. And he concluded that the moon is basically just as rough as the surface of the Earth. The middle one shows his observations of the satellites of the planet Jupiter, and he observed these 4 satellites, and now they are called Galilean moons in honor of Galileo, but he gave them a different name. And for the first time, he observed something that is moving not around the Earth. It is the first time in the history of human beings we are observing something that is not moving around the Earth. The apparent motion is not around the Earth. And this made a significant challenge to the Earth-centered philosophy that was very predominant, especially in Europe, for at least a couple of thousands of years. And he concluded that basically these are satellites of the Jupiter, just like we have the moon as a satellite of the Earth. The right plot shows his observations of the planet Venus, and he observed that just like the moon has phases, which is what we see on the left plot, which is moving from a crescent to the full moon, the Venus also goes through several phases, and he concluded that the Venus is reflecting the light of the sun just as the moon. And more importantly, if you want to explain the observed phases of the moon, it means that the Venus has to move around the sun, not the Earth. So if the Venus was moving around the Earth as predicted by Ptolemy and a lot of astronomers before him, we could not have observed the kind of phases that we see or Galileo saw using his telescopes. So they basically were major nails on the coffin of the Earth-centered view of the universe, and these observations basically supported the Copernican view of the universe, in which the planets were moving around the sun. And we know the history. So Galileo wrote down these observations in a very interesting book called the Dialogue Between the Two Chief World Systems, and in which he challenged the prevalent worldview of the times. And basically, this set of discoveries paved way to this very important intellectual movement called the Enlightenment, and eventually what is called the scientific revolution. And all the modern science that we see today and the technology that resulted from the development of the modern science had its origin in this period. And Galileo's observations had a very, very important role to play in.
Is there a problem? The slides are not moving. Oh, some problem with the slides. They are not moving.
My internet dropped for a second.
I think you can get a better UPS. You can join again, please.
Yes, I will do that.
Yeah, fine.
You see that now?
Yeah, fine. Thank you.
So during the subsequent centuries, astronomers started building bigger and bigger telescopes. And one very important figure in this endeavor was William Herschel in the 18th century. And he, along with his sister, actually, Carol Herschel, made some really big telescopes at the time. So this left one is a telescope that was made by the Herschels, and it had a diameter of about 48 inches, which is more than a meter, like 1.5 meters. So using these large telescopes, they did very important things. One is they discovered the planet Uranus, for example. And one really remarkable thing that Herschels did was they tried to map out the distribution of the stars in our galaxy, the Milky Way. And of course, we know that the Milky Way appears as a strip in the sky because even though it has a shape of a spiral disk, since we are also part of this disk, we see a cross-section of it, we see through this galaxy, and that's why it appears as a disk. Herschel, of course, realized this, and he tried to reconstruct the three-dimensional position of the stars from these observed two-dimensional positions, because he had some way of measuring the distances to these stars using parallax method. And this is the shape or the distribution of stars that Herschel came up with, and it is remarkably close to the actual shape of Milky Way, given the constraint that he had at that time. Of course, it was very difficult for him to leave the human-centric philosophy, so he placed the sun at the center of the galaxy. So this is where the location of the sun is. And we know that it is incorrect now. The sun is located in a very ordinary place, far away from the center of the galaxy. And in the center of the galaxy, there is a supermassive black hole, etc. Something that we have realized in the last 50 years. So astronomers continue to make bigger and bigger telescopes. For example, this is one of the largest optical telescopes that exists now. It's called the Keck telescope. This has a dish of about 10 meters, and there are two such dishes. So you can see a size comparison. There's a rather big American size car here, and this telescope is much bigger than this. So these are kind of the biggest optical telescopes that exist now. There are ongoing plans to build a 30-meter telescopes in which the Indian community is a part of. There's another project to build a 40-meter telescope, etc. So astronomers are making bigger and bigger optical telescopes. However, this is not okay. And we also get the advantage of making bigger and bigger telescopes is that you will be able to collect more light, more photons, and which will help you to to observe fainter and fainter objects, which are or far away objects. And there is, for example, one picture of the optical sky that is a composite picture made by combining several observations by looking at different parts of the sky and combining them. This is not a particularly deep picture of the universe. Basically, you see this horizontal line here, the bright line. Basically, this is our galaxy. So a large number of stars in our galaxy is producing this bright strip. And you see some shadows. These are produced by large molecular clouds that obscures the emission of the stars. This is not, however, the only progress that astronomers have made in the last 400 years. We have also started observing different frequencies of the electromagnetic radiation. And it is obvious to all of you that the light is composed of a large number of fundamental frequencies, fundamental wavelengths, and starting from Herschel and Newton, etc. People have done various observations. For example, you can see these vibgyor colors by passing the light through a prism or a grating. And one very interesting experiment that Herschel did was he discovered the so-called infrared radiation through the following experiments. So what he did was, when you disperse light through a prism, you see the familiar vibgyor colors, starting from violet going all the way to the red. And red, as you know, has the longest wavelength in the visible light. So what Herschel did was he put a thermometer just further away from the location of the red light. And he saw that with time, the thermometer showed an increased reading of temperature. And so he concluded there seems to be some sort of an invisible light that we cannot see using our eyes, but because of this radiation, the temperature is increasing, which is required by the thermometer. And this is now called the infrared radiation, and anyone can do this. This is like a school experiment that anyone could do by making a hole in a cardboard box, and you can put a prism or a grating to disperse the light, and if you put a thermometer far away from the red, after some time you can see the temperature is increasing. So you can detect this infrared radiation. And of course, infrared detectors are much more common now thanks to the COVID pandemic. It happened a few years ago. Most places have now infrared thermometers, and basically the way they work is that every object in a finite temperature is emitting some radiation called the black body radiation. And because our body temperature is of order 37 to 40 degrees Celsius, our body is emitting this radiation in the infrared wavelength. And basically, these thermometers are capturing this infrared radiation to understand our body temperature. So, and we also have infrared cameras that we can do for night vision, etc., etc. It's all trying to detect infrared radiation from hot objects, any object at finite temperature. And we also now know that there is a whole spectrum of electromagnetic radiation, and there is a whole theory of it thanks to Maxwell. And it goes from the longest wavelength radio waves to all the shortest wavelength gamma rays. And they are used for various things like radio communication, microwave antennas, infrared is used for things like measuring temperature or night vision cameras, ultraviolet, sterilizing things. X-rays is used for, probing what is the interior of human body. Gamma rays are used for cancer therapy, etc., etc. So there are various detectors that are used to detect these electromagnetic radiation at different frequencies. And astronomers have used these detectors for astronomy, especially in the last 70 years. So there has been a big revolution in basically observing the sky over its multiple wavelengths of electromagnetic radiation. So here is one example of a radio antenna. This is from the Giant Meter Wave Radio Telescope, which is operated by the National Center for Radio Astronomy of the TIFR. This is located near Pune. This is one of the largest radio telescopes of this kind. And it's a network of radio telescopes. So each telescope is like a 30-meter, you can see a car here. It is much bigger than that. And this GMRT consists of over 100 such antennas that are located in a large area of tens of square kilometers. And it's one of the largest networks of radio telescopes in this meter wavelength band. And unfortunately, so in fact, we can do very good radio observations from ground because the atmosphere is basically transparent to radio observations, to radio waves. Unfortunately, this is not so. Unfortunately or fortunately, the atmosphere is opaque to high energy radiation, such as X-rays or gamma rays. It is good for us because otherwise all these ionizing radiation could cause mutations on our cells and can cause undesirable effects. So in some sense, atmosphere is protecting us from this high energy radiation. However, this means that to measure gamma rays or X-rays coming from outer space, one has to send satellites that go above the atmosphere. Or in the earlier period, these detectors were sent on balloons, which would go above some significant layers of the atmosphere. But now most of the state-of-the-art measurements are done using satellites that go around the Earth orbit. And here is an example of a gamma ray satellite. Here is an example of a gamma ray X-ray satellite, which is named after Professor H. Chandrasekhar. And this X-ray satellite is called NASA. It's called Chandra. It's launched by the NASA. Here's similarly a diagram of the COBE satellite, which is for measuring the microwave background radiation. And one remarkable thing is that if you look the sky using different frequencies of electromagnetic radiation, you get access to very different phenomena. So for example, this is a sky map of optical sky, which I showed earlier. But if you look at the same sky using a microwave detector, an antenna that is used to detect microwave radiation, similar to, for example, our mobile phones, you see a very different thing. So what is plotted here is the intensity or the temperature of the cosmic microwave background radiation. So this is basic. Is there a question, Dr. Ashok?
Yeah. No. Some disturbance, please carry on.
Okay, so this is a plot of the sky map of what is called the cosmic microwave background radiation. This is the very first light coming from the very early epochs of the universe. Just to recap, remember that our best understanding of the origin of the universe is that it was produced in a big bang about 13.6 billion years ago. And the universe continued to expand after that. And the early universe was extremely hot and dense, and hence was opaque to light. Light could not have traveled through this very dense universe. However, as the universe expanded, it cools down, and density also went down. So at some point, neutral hydrogen atoms were formed from the protons and electrons that were moving around with very high speeds, with very high energies. And once the neutral hydrogen atoms were formed, light could travel through it. And basically, this happened about 200,000 years, about 2 lakh years after the Big Bang. It's a very small amount of time as compared to the age of the universe, because the age of the universe is about 13 billion years, while I'm talking about 2 lakh years. And basically, the light that has escaped from the universe, it is still going through the universe, free streaming all the way, is seen as the cosmic microwave background radiation now. So wherever you look at the sky, you see the same radiation coming from all directions. But there are very minute differences in the intensity of this radiation coming from different directions. And just like I mentioned about this black body radiation, basically this is as a black body radiation. In fact, this is the most purest form of black body radiation that you can observe. And you can, just like we can, by measuring the distribution of the the infrared radiation, one could measure the temperature of a person by using a infrared thermometer. By looking at the spectrum of the microwave radiation, we can attribute a temperature of this radiation, and it turns out to be about 3 degrees Kelvin all over the sky. But there are extremely minute differences in the temperature of the radiation coming from different parts of the sky, and that is shown by these blue and red dots. These red dots are slightly hotter regions, and these blue dots are slightly cooler regions. And this difference is like 1 part in 1 lakh, 10 to the minus 5. So it's a very minor difference, but they provide some very important fluctuations in density of the early universe. It basically corresponds to small differences in the density fluctuations in the early universe. And slightly higher density regions eventually became stars and galaxies and us, while these less dense regions, or these cooler regions, eventually became large intergalactic voids.
There is some pause. I don't know, please check it out. We are not hearing any sound or no slide transition also. Some problem with this UPS. Wait, he has to rectify. He will join again. Oh. You will have to join again.
Can you hear me now?
Yeah, I can hear, but the slides are not there. Can you have to share the slides, please? Slides.
I have shared. Some seconds to come.
Maybe it will take some time.
I'll tell you the story. So, if you look at the same sky using a high energy detector, like an X-ray detector, you see a very different picture. You see black holes accreting matter and this heat, this hot gas producing X-rays, etc. So to summarize, basically observing the sky using different frequencies of electromagnetic radiation is basically like having different windows to the universe. You're basically seeing the universe, different kind of phenomena. And there are phenomena that you can observe only in one frequency band and cannot be observed using other frequency bands. Do you see the slides now?
Oh, no. Now it's slide back. Yes, please. Yeah, it's back now.
Okay. Yeah, okay. But all the observations I talked about are using different wavelengths of the electromagnetic radiation. But in the last century, especially after the second half of the last century, astronomers have started using messengers that are different from electromagnetic radiation to observe the skies. And the pioneering efforts are through cosmic ray measurements. Cosmic rays are, they are not electromagnetic rays, they are not rays, they are actually particles, could be protons or nuclei of heavier elements like iron. In fact, the Indian community has made pioneering contributions to the discovery of cosmic rays and using them for astronomical research. This is some photographs of the Kolar experiment that happened here in the same state, Karnataka, in the Kolar coal mines, the deep underground laboratory. TIFR, with a Japanese collaboration, had a lab that was used for very interesting particle physics experiments, and including remarkable discoveries in cosmic rays as well as atmospheric neutrinos. In fact, the first discovery of atmospheric neutrinos happened in this Kolar KGF. There are, unfortunately, this had to be stopped because of the closure of the mines in the 80s or 90s. But there are, the cosmic ray astronomy continues, and there are some remarkable observations happened in the last 2 decades. One is the discovery and observations of these extremely ultra-high energy cosmic rays. These are, again, protons or heavier nuclei coming from outer space, with energy something like 10 to the 18 or 10 to the 19 electron volts, which are millions of times more energetic than the high energy particles that are created in this large hadron collider in CERN, etc. So these are millions of times more energetic than the heaviest energy particle that are created on human laboratories. So there are some remarkable, and this is a one particular observatory called the Pierre Auger in Argentina. It basically consists of a large number of water tanks. It's located in a large area of Argentina. And when these high energy particles go through water, they produce what is called a Cherenkov radiation. And this has been used to detect such Cherenkov radiation and to backtrack these cosmic rays. So I should correct myself. These cosmic rays basically hit the atmosphere, the atoms in the atmosphere, produce a secondary shower of secondary particles. And all these particles, like pions and other things, go through this water and produce a Cherenkov radiation. And by reconstructing the shower of radiation, this cartoon here, the secondary shower of radiation, one can backtrack and point to the arrival direction of the cosmic ray. And here is an example. So as I told you, these are extremely high energy particles, which are millions of times more energetic than the high energy particles created in the Large Hadron Collider. So there seems to be some cosmic particles accelerators that are happening in different parts of the world, of the universe. It is not entirely clear what these are. So they could be basically black holes creating matter and producing high energy, emitting high energy particles, or energetic phenomena including involving neutron stars, such as pulsars or gamma ray bursts, explosions of very massive stars. It is not entirely clear to astronomers what exactly is the source of this ultra high energy cosmic rays. So here is, for example, these black dot shows the arrival directions of these ultra high energy cosmic rays in the sky, and these blue dot shows the non-locations of some active galactic nuclei, which are supermassive black holes are creating matter and producing these, potentially producing these cosmic rays. So we do not see a good correlation between these black dots and these blue dots, and so it is not clear whether these black holes are indeed the sources. But also one should note that these charged particles are affected by magnetic fields, and there are magnetic fields in the galaxy which can deflect them. So the actual directions of these sources may not be the ones we observe. So one has to worry about these things also. So the summary is we do not know exactly what is producing these ultra-high energy cosmic rays, but it is a puzzle, and it is not a surprise because this is a very recent observation in the last 20 years or so. And often in the beginning of new branches of astronomy, one has these questions, and hopefully in the decades to come, we will resolve these puzzles and make more progress. Important milestone in the history of modern astronomy is using neutrinos to do astronomical observations. And here is another remarkable astronomical observatory called the Ice Cube, which is located in the Antarctica. So here is the right plot shows an image of the entrance to the actual detector, but the actual detector is deep underground, something like 2 kilometers of underground. And what these scientists have done is to drill deep holes in the Antarctic ice, which is a remarkably transparent object, and have put these photomultiplier tubes that can detect these Cherenkov radiation. And when these neutrinos go through the ice, they produce secondary particles. They actually produce this no secondary particle. They produce there's some shower of secondary particles, and can produce the Cherenkov radiation, and which can and you can use this to reconstruct these the arrival directions of these neutrinos. This is the sky map of the neutrinos discovered by this Ice Cube observatory. Again, there is a puzzle. It is not entirely clear who's producing these high energy neutrinos. There was one observation 3-4 years ago that astronomers observed the unusual activity of a blazar, a supermassive black hole whose jet is pointing toward us, which is a coincidence with a particular high energy event. So there is a possibility that these neutrinos are coming from such blazars, but it is not entirely clear that is the case. But the important part, again, it's another puzzle because it's a new branch of astronomy and we have more questions than answers. It is important to have these different kinds of measurements because, for example, neutrinos measurements are they can carry complementary observation as compared to electromagnetic waves. One excellent example is the observations of the sun. Right? When you observe the electromagnetic waves of the sun, these rays are produced on the surface of the sun from its corona, etc., etc. While if you want to see the interior, one has to observe neutrinos. The neutrinos are produced in the interior of the sun. As you are, the only way of seeing what is the interior of the sun is through observing the neutrinos. So they contain complementary information. So now which is the gravitational waves. So gravitational waves are different from electromagnetic waves as well as particles such as cosmic rays or neutrinos. They are ripples in space-time. They are freely propagating oscillations in the curvature of space-time. And their existence was predicted by Albert Einstein about a century ago as a consequence of his theory called the general theory of relativity, which is a theory of gravity, and it describes gravity as a curvature of space-time. So any massive object can curve the space-time around it. While if these massive objects move with an acceleration, they produce disturbances in space-time, ripples in space-time that propagate at the speed of light. And when these waves pass through the Earth, they change the geometry of our space-time. They create small disturbances in the geometry of our space. And we measure these small disturbances, these extremely tiny disturbances, using these very large antennas called the laser interferometers. And this is two photographs of the LIGO observatory in the USA. LIGO stands for Laser Interferometer Gravitational Wave Observatory. These are, for the physicists in the audience, these are large Michelson interferometers. with arm length of 4 kilometer by 4 kilometer. So these are so you can see the cars are like this. So when we don't see the end of an observatory here, because we only see the corner station of this hill, while so the beam tubes which reflect laser light, and each of them have a length of about 4 kilometer, exactly 4 kilometer. And there are two such observatories in two different corners of the USA, separated by about 3,000 kilometers, and they made the first direct observation of gravitational waves in 2015. And this is a plot of the observed gravitational wave signal. And by studying this, we have concluded that this signal is produced by the collision, the merger of two black holes that each weighing about 30 times the mass of the sun. Two massive black holes, each weighing about 30 solar masses, moving around each other in a binary orbit, emitting gravitational radiation. And as a result, they could come closer and closer and eventually merge, eventually collide to form a much more massive black hole that would oscillate by emitting this quasi-normal mode frequencies. Like these perturbed black hole emit a particular kind of radiation called quasi-normal radiation, which was first calculated and predicted by C. Vishweshwara, who is our Indian scientist born and brought up in Mysore and Bengaluru. And he was here, in fact, in Bengaluru to see the announcement of the first discovery and made a remarkable legacy as a scientist, as a science communicator. So, and the three founding scientists of LIGO, Ray Weiss, Barry Parish, and Kip Thorne, were awarded the Nobel Prize in 2017 for decisive contribution to the LIGO detector and the observation of gravitational waves. But this is not the end of gravitational wave studies. In fact, the idea is that we can now use these observations to do astronomy, just like neutrino astronomers and cosmic ray astronomers have been trying. And so far, we have detected about 200 gravitational wave signals coming from such mergers happening at different parts of the sky. These numbers are slightly outdated because LIGO is collecting LIGO underground collecting data as we speak now, and we are detecting events every week. We are detecting new signals almost every week now, and so far over 200 gravitational wave signals have been detected, and each are produced by the merger of two compact objects, black holes and neutron stars, happening at different parts of the universe. And here is a slightly old picture of the black holes and neutron stars that we have discovered through gravitational wave observations over the last 8 years. For example, this one shows in each, there are three blue dots here, and the vertical axis here is showing the mass of these black holes in units of solar masses, in the units of the mass of the sun. So here's a cluster of three objects. This means that this gravitational wave signal was produced by the merger of two black holes about 25 and about 40 solar masses, and they merged to produce a more massive black hole of about 60 solar masses. So each of this cluster is computed from one observation of gravitational waves. In contrast, these red dots are the black holes that we have observed from our own galaxy through X-ray observations. And you can see that on average, the black holes discovered by gravitational observations are significantly more massive than the black holes in our own galaxy. This was actually a big surprise to most of the astronomers, because most of the astronomers were thinking that the black holes produced by the collapse of stars would be order 10 solar mass. But now we are seeing 50 solar mass black hole, and even black holes much heavier than even 100 solar mass. So there is an indication of much more a new population of black hole that we have not appreciated the existence of. Similarly, these are the neutron stars. The orange dots are the neutron stars observed by gravitational waves, while these yellow dots are the neutron stars in our own galaxy that are observed by radio observations. And just remember that Black holes and neutron stars discovered from gravitational observations are coming from very, very far away galaxies, very, very distant, hundreds of megaparsecs away, hundreds of millions of light years away. While all these neutron stars and black holes are from our own, discovered by electromagnetic observations, are from our own galaxy. So we are really probing cosmic distances using gravitational observations. And there are a large number of very interesting signs have come out of these gravitational observations. They have really established a new branch of astronomy. The first time they are observing binary systems of two black holes and a black hole and a neutron star. These are the first observations of solar mass black holes that are more massive than about 30 solar masses. There is potential evidence of what we call the intermediate mass black holes, or black holes that are more massive than about 100 solar mass, but less massive than this million solar mass black hole that we observe in a galaxy and the center of our galaxy. There was one remarkable observation of a binary neutron star merger that happened in 2017, and this was seen. We observed first the signal of this in spiral of these two neutron stars in gravitational wave observations. And subsequently, this collision of these neutron stars produced a large flash of electromagnetic radiation, first as a gamma ray burst, and through that called a kilonova and radio afterglows. So we observed these things. Astronomers across the world observed the emission, electromagnetic emission from this merger through a variety of different electromagnetic frequencies using a variety of ground-based and space-based telescope. And it is, in fact, one of the first remarkable multi-messenger observations of one single astronomical phenomenon. And using these observations, we are able to uncover some very interesting aspects of neutron stars and their astrophysics. For example, we now know that the short gamma ray bursts are produced by the collision of neutron stars. We have some constraints on the equation of state of this dense nuclear matter from the observations of this particular source. And the electromagnetic counterparts coming out of this merger have provided some very tantalizing hints on the origin of heavy elements in the universe. We know that the elements lighter than the iron are synthesized in the core of stars. But how did elements heavier than iron come out in the universe? Until very recently, about 2 decades ago, the speculation has been that they are produced in supernova explosions. But more recent estimates, in fact, challenge these things, because if you can look at the abundance of the supernova in the universe and the calculations of how much heavy elements are synthesized through nuclear fusion in this, not nuclear, this is called the arc process synthesis in this supernova, then it turns out that we could not explain the observed abundance of heavy elements purely using a supernova explosion. And the mergers of neutron stars was proposed as another candidate. And these observations, in fact, concluded that it isn't the case. And now, there are estimates that show that, in fact, a significant fraction of the heavy elements, such as gold and platinum and other things, in the universe could be produced by the merger of double neutron stars that happened in the past. There are estimates suggesting that about one Earth mass worth of gold was produced in one neutron star merger itself. So it's a fun story to quote. It's very hard for me to summarize all the science came from these observations in this last 8 years, but there are very nice summaries of the popular summaries of the science from each paper from the LIGO scientific collaboration. So you're welcome to look at some of these web pages, which provides a list of such things. So the remaining 5 minutes, let me summarize what is the prospect, what is happening in the next decade or so. One thing I want you to notice is that gravitational astronomy requires a worldwide network of detectors. Using a single detector, we cannot localize the source in the sky. And that is done by combining the data from multiple detectors. So this is something like similar to how we localize the origin of sound using our two eyes. We cannot localize the origin of sound by using this one eye. And there is an existing network of detectors in Europe, in US and in Europe, and one coming up in Japan. But they're all located in the northern hemisphere. And if you had one that is closer to the equator, we will significantly improve our ability to localize the source of gravitational waves. And that is the idea of this upcoming detector called the LIGO India, which is aimed at building a LIGO detector in Indian soil. And it is in a very active phase, and the construction is about to begin. So all the land is acquired, and we have done a prototyping of the technology, etc. And it's a collaborative project involving the Indian institutions, the IUCA, RRCAT, IPR, and the Department of Atomic Energy and the Department of Defense Technology. There's an active collaboration with the LIGO observatories in the US, with a proposed timeline in the next 5 to 10 years. There are also plans in the next 2 decades to build next generation of the gravitational detectors. Sometimes some will be in underground, we have a better sensitivity, or its sensitivity 10 times better than LIGO observatories by building much larger versions of LIGO. Similarly, there are also these are all focusing on this one particular frequency band of the gravitational spectrum. It's about 10 hertz to about a few kilohertz. While we expect gravitational waves to exist across different frequency bands, then there is an ongoing planned space-based detector called LISA, which is by the European Space Agency, which is to build a gravitational observatory in the space, which will detect much longer wavelength gravitational waves or much shorter frequency gravitational waves that can be produced by these merger of supermassive black holes at the center of galaxies, etc. It's called LISA, with a planned launch date in 2035 or so. There are also very interesting ideas of building decihertz gravitational waves detectors, gravitational waves in about 0.1 hertz. There are very interesting ideas. For example, one idea is to use build space-based detectors like the LISA. And one very cute and cool idea is to use the moon itself as a gravitational detector. The idea is when the gravitational waves go through the moon, that will perturb the moon and it will shake the moon. This very small shaking. And the shaking of the moon can be measured using seismometers that are placed on the moon. So, to summarize, in the next few decades, we observe gravitational waves across its frequencies. So there is a spectrum of, instead of a cartoon spectrum of the gravitational waves, just like we have the spectrum of electromagnetic waves. The longest wavelength of gravitational waves could be as large as the size of the observable universe, while the shortest wavelength could be, kilohertz or even megahertz also. And we can think of various kinds of phenomena that could emit gravitational waves across this frequency band. And in the next decades, astronomers will be probing the spectrum in different frequencies using different kinds of techniques, very similar to what astronomers have been able to do in the early 20th century. So to summarize, the modern astronomy began about 4 centuries ago with the discovery of the optical telescope. And in the last century, 20th century, astronomers expanded the scope of astronomy across the wide frequency of the entire wide spectrum of the electromagnetic radiation. And again, the late 20th century, astronomers also have used non-electromagnetic messengers, those cosmic rays and neutrinos, to probe the cosmos. And the recent observations of gravitational waves by LIGO and Virgo have opened up a new branch of astronomy, and we expect hundreds of gravitational wave detections in the next few years and millions of gravitational detectors in the next decades. So really, opening a totally new branch of astronomy. And it's really a new window to the cosmos. So let me stop here and happy to take any questions.
Thank you very much. We'll take a few questions on this occasion.
Absolutely, yes.
Anybody who wants to ask any questions or make any comments, you can raise your hand and do so.
Yes, sir. I want to ask some questions.
Yes, wait. What's the question? Yeah, please ask.
In the basic, atom is the basic thing for the non-living bodies, and from there all type of